Anyway, I'm very much enjoying being here and providing what I know about combustion to the next generation. It's really interesting, fun, and nice thing to do. So we will continue today also on premix flame, and the topic is premix flame in closed vessel. And we are going to start with a equation that we derived before in first lecture, or in the first day rather, which are the general equations for the low Mach number combustion, right? In other words, again, the flame propagates slowly relative to acoustic waves. So acoustic wave, the Mach number is the ratio of the flame speed to the speed of sound. So small meaning speed of sound is very fast compared to the flame. So they propagate fast and they equilibrate the pressure throughout the vessel. They don't affect the combustion. In reality, of course, they do, and they can bounce back and forth from the wall and change things. But, the simplification adopted to understand the first behavior of the flame is within that context. And in the low Mach number approximation, we saw that the major thing is that the pressure is written as the mean pressure, P of t, depend on time only. That's the pressure that get equilibrated, plus a dynamic pressure that enter into the momentum equation. And so then in the energy equation, the only contribution to the work come from the mean pressure, capital P, okay? And we have seen the derivation of this equation include whatever it's scaled with respect to the diffusion lengths, the flame speed for velocity, and time is scaled with this length, and the L here should be L sub D. It's quite clear. It's a typo, and that's what the idea is. Now, in a vessel, the combustion can be very rapid or very slow, or relatively rapid or relatively slow. If it's very slow, what happens is the burning occur everywhere in the vessel, and it looks like more as a well-stirred reactor. That's not the type of problem that we are looking here. We are looking at a situation where when you ignite, there is a flame that separates the unburned material from the burn, and that flame propagates through. So it's a relatively slower process, let's say. So these are the equation, and we are, just to remind you, that in this equation, the capital P here, or the mean pressure, is obtained by integrating the energy and the continuity equation. When you add them together, you get this, thank you, you get this equation. When you integrate it throughout the volume, you get this equation here. The only thing that was used is that the divergence theorem, that instead of the integral of divergence V, you get the flux through the surface of the vessel S. And the same thing, the Laplacian is the divergence of the gradient. You use divergence theorem, you get the gradient dotted with the normal. And if there is no heat loss, if you assume that there are no heat loss, this term is zero. And since the velocity is zero on the wall, then this term is zero, and you get an expression for the pressure. Of course, if there is heat loss, you have to account for them from this term. And so we have seen that this is the equation that describes the pressure buildup in the vessel. Now, the next thing that we can do is that if we combine, let's say, for lean condition, the fuel and the temperature equation, to again eliminate the reaction term. Remember, we can always combine them such a way that the reaction term cancel. what we get is what you see here. And you can rewrite this equation as a time derivative of this quantity, which is a sort of an enthalpy, if you like, associated with the fuel, equal to this term, which is, you see the P does not depend on the volume, so it's just integration of the volume. And if you integrate this from t equal to 0 to the n time meaning when the flame have reached the end of the domain and all the fuel is consumed, okay, we're assuming that it's all consumed, then you can get an expression for the end pressure, which is not very surprising. You can actually do that from thermodynamic consideration. You consider the initial state and the end state, and you get that. So anyway, the important thing is that we know what the end pressure. Note, by the way, gamma is like 1.4, Q is the heat release, which is like 7, 8. So the pressure rises significantly by a factor of almost 10 throughout the propagation. Now, in order to describe in more detail the propagation, we're again going to use the hydrodynamic model. In other words, we're going to assume that the flame is relatively thin compared to some other scale in the problem, so that all diffusion effects, okay, like viscous diffusion, heat conduction, fusion of reactant, all occur in the thin flame, outside of which you just have the Euler equation, if you want, the continuity. I neglected gravity in this study, as you see. And so what you have is the continuity, the momentum, and the equation of state. And here's the energy equation. Remember that term came from the work that is not zero. Yesterday, we only spoke about freely propagating flames, so P was essentially the ambient pressure or the atmospheric pressure. It was equal to 1, so this term did not come into play. That's where the pressure buildup is affecting the temperature and the density of the mixture. And then across the flame, you have to satisfy the Rankine-Hugoniot relation, and I added here the relation that relates the temperature and the concentration of the reactant, that we assume here only one reactant, and let's say the fuel if it is a lean system. And so this is mathematically the problem that we want to address. Now, remember yesterday when we talked about the hydrodynamic model, it was simple to deduce that on the unburned side, you have one density, the unburned density. On the burned side, there is one density, which is the burn value. And the ratio was known. It's essentially related to the amount of heat release during combustion. But now the density is not a constant, because the gas gets compressed as the flame propagates against the wall, both in the unburned and the burned gas, and so in the burned side. And so we have to see how that play a role. So if we, just a minor comment that from these two equations, and that's why I wrote it on the same line, it's easy to deduce that the divergence of V equal to minus 1 over gamma P dP dt. In other words, all you do is just replace rho here and T here by the equation of state to get that. What it tells you is that the compression is associated with the pressure buildup, right? And so this is important to observation, at least to see. Why is it important? Well, if you're doing a one-dimensional problem, as some of the examples that I will do, then essentially that equation determines the velocity, because there's only one component, so the divergence just du dx, du dr, depending on the geometry. But if you have a multi-dimensional flame, it's not sufficient, because that's one equation for 3 components of velocity, so you cannot deduce the velocity from here, you have to go back to the equation, to the momentum equation as well, and so it's more complicated, right? Okay. So before we continue, the y satisfied dy dt equal to 0. So if the initial mixture is homogeneous, then on the unburned side, y is known. It's y naught. And on the burned side is all consumed, so it's equal to 0. What about the energy equation? The energy equation, when you combine it with the equation of state, you can deduce that d by dt, material derivative, of this quantity equal to 0, okay? So what it says that this quantity that I denoted by E is conserved along particle path, okay? And that quantity is in fact related to the entropy. When I say related, the entropy is the log of this multiplied by some coefficient. So I will call it an entropy function. And so the entropy function is conserved along particle path. And the entropy function is either from this relation can be expressed in terms of temperature or in terms of the density, of course, if we know the pressure. Okay. And across the flame, since there is a jump in temperature, so there is also a jump in entropy. And so the entropy jump is deduced from the appropriate relation for the temperature, and it's equal to Q divided by P gamma minus 1 over gamma. Note, by the way, that if combustion occurs in free space, P is 1 everywhere, so the jump in E, which is nothing more than the temperature, is just Q, as we had yesterday. So everything simplified to whatever is needed. Now, so the conclusion of this is that the state of the gas can be expressed as in this box. On the unburned side, the entropy is initially 1, and since all particles conserve that quantity, it's 1 everywhere in the unburned gas. In the burned gas, it's dependent on space and time and need to be computed by this material derivative equal to 0. And then once you know E, you know rho from the simple relation here, and you know T as well. So the only unknown to add to the other equation, other meaning Euler and so on, is the entropy on the burned gas. One more thing that we can deduce from here at the moment is the flame temperature. The flame temperature will be defined as the temperature just on the burn side at the flame. So it is going to be P gamma minus 1 over gamma times the value of E at the flame. But the value of E at the flame can be obtained from the jump relation, because the jump tells you it's E at the flame minus 1 in the unburned gas. And so when you put it in the relation, it's what you see here. Don't be confused that Q does not appear here. It does appear. I just wrote the first part as the adiabatic flame temperature to show the change in flame temperature from the freely propagating flame. Instead of having the flame to be, the temperature to be the adiabatic, now the flame temperature increases. When P is 1, it's just that, and then it rises. Okay, so this, now that we know the state of the gas, well, we don't know it completely. We still have to, of course, solve for E. We can solve for the velocity and so on from the momentum equation, etc. Now, in a similar way as we discussed yesterday, the problem was analyzed inside the thin flame to deduce what is the burning rate or what is the propagation rate of such a flame. And so now here is some notation. The internal flame structure provided the burning rate, M star meaning M evaluated at the flame just ahead of it, because remember, flame speed was conventionally determined as the propagation speed relative to the incoming flow. And so here is the incoming flow, propagation speed. This is what we call the flame speed. You multiply by the density. Rho u is not constant. It's the density of the unburned gas just ahead of the flame. Remember, the gas is going to be compressed, so rho will change. Rho u is the value, the momentary value just ahead of the flame. And when you determine a flame speed relation, you obtain the following expression, which is a bit, actually it's a very recent result published in JFM, and it's just a little more complex than the one that we have seen yesterday, which is the flame speed relation to flame stretch. Note that when P is 1, this M here, which I would refer to it as the burning rate of a planar flame, which we are going to talk soon, is, you see, it's a deviation from the adiabatic temperature because the flame temperature changes. So, and this ratio comes from the density, essentially. So what you have is capital M is the burning rate of a planar flame. You divide by rho u, you get the flame speed of a planar flame. And this is the contribution of order delta. Delta is the flame thickness, and those are the stretch effect that I discussed yesterday. Now, there is a coefficient here, which is the Markstein number, similar to what we talked yesterday, depend on the Lewis number, the mixture properties, and so on. K is exactly the flame stretch that we talked about yesterday, and but there is more contribution, which is m dot over m and p dot over p, dot meaning, just for simplicity, d by dt. It's a notation for the time. Remember that m, the burning rate of the planar flame, depend only on time, because Tf vary from Ta only. It's only, it depends on the pressure, which only vary in time. So this is the relation. Now, I denoted this K minus m dot over m as K sub V. And I would explain that first. So first, before that, I want to tell you the meaning of this m dot over m. So the temperature now in the preheat zone, when you do the analysis, instead of being a simple exponential, as we discussed yesterday, turned out to be e to the m eta. M appeared there, okay? And remember that this is the profile, so when change m, you change effectively the thickness of the flame. And so it turned out that m is inversely proportional to the flame thickness, not the scale diffusion length, but the actual flame thickness. And so m dot over m will be the time rate of change of the flame thickness, as you see here, and the reason it's minus because when m increases, the flame gets thinner. So, okay, so what you have, remember K, the flame stretch, what was the time rate of change of the area of a surface element, right? So now what you have is the area of the surface plus the volume or the thickness of the flame element, which is the volume of the flame element. So in this study, we have seen that the whole thickness of the flame and its transverse extension, deformation during motion enter into this relation. Actually, it's a first example, even though the idea of what I refer here to as volumino stretch has been introduced before, but really it's the first example that show that it appears in the analysis. In other words, that the burning depend on that quantity. I mean, hypothetically, you could have assumed this as being correct the formation, right? Not only the area. So why didn't it appear yesterday in the analysis? Very simply because the analysis of a freely propagating flame under the assumption that discussed yesterday, the thickness is constant. So it does appear, but it doesn't affect the volume. So anyway, this is what this is, and then we complete, of course, the discussion by this equation that I discussed earlier, give us the pressurized. So completed because before we had, remember, an integral of the reaction rate throughout the whole volume. So here it will simplify to just, to leading order at least, the burning rate, which is M, and AF is the area of the flame. So if the flame is simple, we know the area. Simple meaning planar or spherical, we know the area if we know the location. If it's highly corrugated, you have to numerically evaluate the surface of the interface. Okay, so the first example is a planar flame. And the planar flame, the velocity is very simply deduced. I will take you back quickly. Oh, don't tell me it's not going to work now. So, maybe I'm too far from, oh, here. Okay, next, here. From this relation, you see in one-dimensional case, this du by dx, and so it's very easy to integrate to get the velocity u. Of course, in terms of p, which we will be determining later. So this is a planar flame which is propagating from the left to the right, and the velocity turn out to be depend on the p dot over gamma p essentially is the compression rate I told you earlier, and L minus X, L is the length, and minus X. So the gas, the burn gas, as before, expand due to the heat release, temperature rise at the flame, the density increases, and so the gas expand, and then it moves to the left. But now it doesn't have an infinite space to expand to. It is compressed by the wall, and so this is what this is how its value, its compression rate times X, and then the flame pushes the unburned gas towards the other wall, and so this is the motion in this two direction. And you can evaluate the flame position by mass conservation across the flame, and this is the flame position, again, in terms of P. So we still have to determine P, and I don't know why this thing doesn't go my way today. Okay, here it is. So to determine P, we need to determine the entropy, and the equation for the entropy is written here. Remember, it was a material derivative, so it's the EdT plus V, right, which is V, the EdX, so this is the entropy in the burn gas, and you compute E from this PdE. Turn out it's just a function of x p to the 1 gamma, and this function can be determined by the proper jump relation at the flame. Anyway, this is a mathematical detail. By the way, the solution of this obtained by, it's called method of characteristics. It's for first order PdE. So anyway, it's not the...
I don't mean to interrupt, but I'm looking for somebody named Prosper.
I don't know.
Okay.
Oh, you got it. Okay. So, so we know the entropy E. So if we know the entropy E, we know the temperature and density, and I will show you plots of this in a few minutes. So now here is the burning rate, M, as we had before, and this is just to put all the equation that we need to solve. And now here are the solutions of this simple equation. The pressure rises, as you see, quite significantly. Of course, depend on the heat release. The larger the heat release is, it rises larger, and as I told you, for realistic value, it can be almost by a factor of 10, as you can see here. And m dot is the mass burning rate, or the burning rate, if you like, and the burning rate also increases starting from 1. The assumption is, I maybe didn't say that, is that initially we put a planar flame as the initial condition, and we let it propagate. In other words, we're not describing the actual ignition process and so on, okay? Then here is the velocity field at consecutive intervals of time, or constant interval of time. What you see is initially is the blue curve. This is the planar flame almost at time t equal to 0 when we put in. So it jumped, probably the solution was with Q equal to 5. So you see there's a jump of 5. And then the temperature in the, the velocity in the unburned gas is not a constant as it would be in freely propagating gas because of the compression and because it has to go to 0 at the other wall. So it decreases as you see in the blue curve. Now, for later time, we can follow this curve, let's say. So here is the velocity increase across the flame, and then the burn gas moves to the left, right? Negative, go to 0 at the wall, and the unburned gas moves to the right. So these are the velocity profile. This is the density profile. Again, initially, you have a known density, 1, say, and then it's constant behind the flame. No, it wasn't 1. I don't know what's the initial value, sorry. But anyway, what you see is that at later time, as the flame moves to the right, the density of the unburned gas increases, in fact, increases significantly, whereas similarly, the density of the burned gas, which is pushed to the left. Actually, this is correct. What I didn't, I can correct myself now. You see, what you see here is the density of the unburned gas. I simply forgot that unburned is to the right when I see this picture. So the blue curve is rho U is 1, the unburned gas. And this is the unburned gas, which is the lower value due to gas expansion, right? So it lowered to whatever factor. Okay, the temperature, which is the next slide, is actually more interesting. When the flame is here, say, you see the unburned gas is at a temperature. Note, by the way, that the temperature, and this is also true for the density, in the unburned gas, it changes only in time, but not so much in space. In the burned gas, it also changes in space. But anyway, this is a detail. What you see is a rise in temperature due to the combustion at the flame. Note that the flame temperature is increasing a little bit. From here to here, it's a larger jump. Maybe it's not obvious, but if you measure it, we have seen the expression that Tf is larger than the adiabatic temperature. But more interesting is that the temperature keep increasing from the flame on the burn side of the flame. This is not due to burning, because all the burning was assumed to be at the flame. This is due to adiabatic compression. So the gas gets compressed, the temperature keep on rising near the wall. And in fact, there are experiments I didn't see a nice, I didn't have, I mean, I've seen a nice picture of that. It's typically referred to as the Flamm-Mach effect. It's not Mach from the Mach number, spelled also differently. Anyway, you can search it in the literature. It's a very old experiment that was observed years ago. Usually it's observed in spherical flame, which an example that I will discuss soon. So you ignite the mixture at the center, you let it propagate out, and then you see that the brightest spot in the picture is actually at the center and not where the flame is. The flame is bright, but at the center it's brightest, which is like what you have seen here. This is the propagation speed, xf dot, and the flame speed. There is a difference between the two. Propagation speed is the time rate of change of the position of the flame. The flame speed is relative to the flow. So we see that the dotted curve is the propagation speed. Of course, the flame advanced from left to right, and it moved faster as it got to the right. And the flame speed, in principle, because of the higher value of Qs, it usually decreases. The reason it decreases is because the flame have to confront a denser gas, and so relative to the gas, it moves slower and slower and slower. Okay? The next example is a spherical flame. The analysis is quite similar, but the form is a little different. So again, we ignite the flame at the center. This is the flame. The unburned gas is pushed away towards the wall of the vessel. And now the burned gas is moving in towards the center. In a freely propagating case, the burned gas must remain at rest because it comes from satisfying the continuity equation that the divergence equal to 0, implying that U must be constant, otherwise there will be a discontinuity or a singularity at R equal to 0. Here that's not the case because you see the burned gas move at a velocity proportional to R, so at R equal to 0, it goes to 0. And it's negative, so it moves in. It's positive here, it moves out. This is the position of the flame. And again, we can compute the entropy in a similar way. Remember, this is the velocity of the burned gas, which just bring me to the attention that one of the previous slides, when I show you for a planar case, it seems like the minus was missing. I wondered why is it plus and not minus, but I didn't want to interrupt the discussion, so I didn't say it. But clearly it should be minus because the velocity in the burned gas is negative even there. So if you want, correct it. And then if you know the entropy, you know the density and temperature, and you know the burning rate and so on. And here is a similar figure for the pressure and for the burning rate and the density. Again, it's similar to what I have shown you before. You see, this is the initial density. By the way, unlike the planar flame, numerical computation of this equation, where we started the flame very, very close to the left wall. In the spherical case, you have really to start assuming a small circle, and you cannot take it very close to 0, just numerically it doesn't work well, and so you see that initially we started a little off. But it's a large vessel. On purpose, we took a large vessel to understand the feature there. And that's the temperature. Again, note that there is an increase in temperature towards the center, the Flamm-Mach effect that I mentioned earlier. Okay, in fact, here is also the year I didn't put it in the previous slide of that publication. And now is an interesting result that that come from the flame structure itself. So, which is something that I did not say anything about in the planar flame because it doesn't really affect the flame very much. And this is essentially due to flame stretch. The reason is a planar flame is not stretched, and so those effects don't play a significant role. The only role that it will be in the planar flame is the thickness, which is part of the voluminal stretch. But here, the spherical flame, as it propagates, stretch. And so that is interesting what is happening here. And so here is the velocity where we have assumed a very large vessel. And so the velocity field is given here. But I want to focus on this correction here, which is multiplied by the Lewis number, the effective Lewis number, and the flame stretch, which we have discussed yesterday. And delta is the flame thickness. So note that when delta is, say, this value, 0.05, which is a realistic, say, number, what you get is, you see there are two curves, and one of them account and the other one does not account for stretch. Now, to the best of my memory, the one that does not account for stretch is the solid one compared to the dashed one. In other words, because of the negative, it just sort of delay the propagation, okay? I think that this is what it is. The main point here is in the next slide, really. When delta become very small, those two curves will be almost sitting on top of each other. In other words, the effect of the flame thickness does have a role in the advancement of the flame. Oh, here it says, the dashed line corresponds to the leading order solution, absence of stretch effect. I think I said that this way, but if not, this is the correct way. And the solid line is a solution with the order delta contribution included. Then there is another interesting remark, and this is in this graph. Now, the left curve is the result that we discussed yesterday. And I showed you that depending on the Lewis number or depending on the equivalence ratio, the flame may either decelerate towards the asymptotic value, which was R dot equal to essentially sigma times the flame speed, laminar flame speed, sigma being the density ratio. So usually it's about 7 for, say, sigma equal to whatever, 6, 7, should be 7. Then, and depending on the Lewis number or equivalence ratio, it may either decelerate or accelerate. This is what we have seen yesterday. So if you, and I said also yesterday that people do an experiment which they ignite the center at they ignite the mixture at the center of the vessel and see how it propagates. And after sufficiently long time, when stretch effect become almost small and minimal, which is in this region, they measure the burning rate, and they can, from it, deduce the laminar flame speed. Just divide by sigma, right? But this is true if you're really doing it in a freely propagating setup, because look what happened in a closed vessel, then eventually compression effect will play a role. So people that doing experiment have tried very hard to establish situation where the pressure does not change very much in the vessel. Or if they are actually doing it in a closed vessel, they take only measurement up to a certain distance where the flame is not very much affected by the compression effect. And the compression effect can be measured by the pressure buildup. If the pressure did not build up significantly, probably then the compression effect are small and so on. So you see how these ideas play a role in how you want to design your experiment and design your measurements. If the flame thickness is not so small, but let's say differently, if the vessel is not as large, which is the equivalent thing, then this is the curve that you will get. And you see there is barely a region where there is a nearly approaching an asymptote that you can evaluate the flame speed. So this is an important aspect of observation that should play a role in experiment. There is another one which is not discussed now, but is going to be talked on Friday, is that these flames tend to become unstable. So at some point during the propagation, at some distance, we will see, they start to get corrugated. And when they get corrugated, the speed is no longer what you can deduce from the laminar flame speed. So you have to be also careful about that. So there is a range of condition where you can do your measurement without being affected by those other aspects. Okay. Just to show you that we have actually also computed, or we have constructed a methodology, a numerical methodology, to solve this free boundary problem, as I told you yesterday, which in fact it just appeared online yesterday in Combustion and Flame. And the methodology allows you to compute flame of different shapes. In general, three-dimensional, but most of the example we did is two-dimensional. And this is just a validation that the analytical expression, which are the dashed curve, are more or less constructed correctly, even numerically. You see, numerically, you have to devise multiple things, because what you have to do is when you have a discontinuity, it's difficult, because two ways to solve the problem. You can say, okay, I'm going to solve the unburned gas, I'm going to solve the burned gas, and try by iteration to make sure that the jump conditions are satisfied. But this is actually difficult to do because those iterations don't converge so quickly and so on. Another way is to do what is referred to as a diffusive layer. In other words, what you say at the discontinuity, you smear it numerically with something like a tangent hyperbolic or some artificial way. It's not the true happening in the flame zone because you are consistent with the model, which is the hydrodynamic model. But nevertheless, this is a way to capture the flow before and after. And when that region where you smear the discontinuities become thinner and thinner, then clearly it's better and better approaching. But of course, there's a limit how thin you can make it. Create numerical instability and other things. So there is a play here between getting those things in the right way. And you can see that it's pretty good because it captures the jump size. Maybe it doesn't give you the location as in the analytical form, but it's within a very small distance away. And this is the density here, and this is the same thing for the circular flame, which is the equivalent of the spherical, but of course the formula have to be a little bit adjusted because the continuity equations, spherical coordinates, circular coordinates are a little different, but the results are easily obtained. Okay, and this is to show you that we don't do it only for spherical, but even allow for corrugation. So you see this is a case where the flame remains spherical during the entire domain, whereas here towards the end it gets corrugated for various reasons. Actually, it's a spontaneous corrugation and it's an instability. Again, we will talk about that on Friday. And here is another example of a different nature of a combustion in a closed vessel. It's referred to as a tulip flame in the literature, but I want to say something about that because, first of all, let me explain the phenomena. So those are snapshots of the flame on top of each other as it propagates. Initially, you ignite the flame at the left end of the vessel. So you ignite it with a small kernel, okay? Now, you ignited a small kernel. Initially, the flame doesn't know that there are walls, so it will, presumably due to the symmetry, will expand as if it was a spherical flame, but being near the wall as a hemisphere. So the beginning of the flame will be a hemisphere. That's what you see here, until it hits the wall, right? And then this is the flame in the next time. It's almost here, tangent to the wall. And then suddenly it flattens out. That I'm just describing to you what you see in the experiment. There are also movies of this. And then it flips so that the center of the flame go towards the center, as you see here. And because of this nature, it was called the tulip flame. Unfortunately, in the literature, many places, people that see a flame that looks like this, they call it tulip flame. Okay, you can call it whatever you want. But it's not the phenomena that is intriguing. The intriguing phenomena here is that the flame propagates in a certain direction, then it flips. That's the idea, or that's the importance. In fact, people have used this example to validate numerical simulation. You build a code that it's a reacting code that's supposed to do everything for you. If you can describe such a phenomena, there is some validity that the code is probably covering, quite wide combustion behavior. If it doesn't, question why. Of course, there are many also questions of why the tulip flame forms and so on. And there are controversy comments rather, in the literature about what's the source of that, and that's not my purpose. I wanted just to show you that some of the recent numerics that we have done show that, but I will not elaborate more on this simply because they are really preliminary results. And, preliminary results are nice. They seem to describe everything, but you have to systematically check that, what happened if you change the length of the vessel, what happened if you change the condition, and then you have sufficient confidence in what you have seen and not just jump on it from the beginning. But you see, here is the idea. We started the flame. By the way, now the walls are walls, so there is zero velocity, no slip at the wall. So we're using not just the Euler equation, but the full Navier-Stokes equation to accommodate for viscous effect as well. And but actually it turned out that in the literature there's some discussion that viscous effects are not the main contribution to that tulip formation. One of the idea that we have proposed years ago based on a so-called Sivashinsky type equation, which is a simple equation that can be derived for a weak change in density, is a vorticity creation in the burn gas. And in fact, this picture shows that it's not inconsistent with this. But anyway, you see that the flame propagates as a hemisphere. This is the unburned gas pushed away. and then you see the creation of vorticity or vertical two eddies, say, produced on the burn. And in some sense, those eddies cause that inversion of the flame. I'm not going to say more about this again. It's preliminary, but it just showed that the methodology, the numerical, can be applied. Okay, not sure what is. Oh, there are a few things about propagation in long channels, not necessarily closed. I'll cover a few of those. Again, I never know what's the time. We started 1:45. Help me out. What is the time? It's weird that it's, I teach usually from the hour until 50 minutes to the hour. So we are, I'm not going to cover everything here. So I'll maybe do 1 or 2 slides and then I'll take a break. So this is a very long channel, and we want to take into account how the flame propagate in it. And the main idea here was that we scale things such that A, being the height to the flame thickness, is small. Now, this is maybe not very appealing because the flame thickness is very small, is quite small, and to say that the width is comparable to flame thickness is maybe not ideal. But nevertheless, it's a model that have interesting result. And the main thing here is that when you assume that when A is small, happened. Okay, when you assume A is small, then the continuity equation remains the same. From the momentum equation, you get from the vertical one, dp dy is not balanced of anything because you see A to the 4, A is small, 1 over A is large, so dp dy is 0. And then dp dx is balanced by the second derivative of u is the axial velocity. And so essentially, what you have, P is independent of Y and is determined from this relation. It's like a Poiseuille flow. Okay? So all I wanted to say here is that what you have, the flow in the channel, behave like Poiseuille flow. But Poiseuille flow, you dictate the pressure on the two sides. Here, the pressure is not known, and what you determine the pressure is from the combustion field. So when you do this, you get details and so on. You get an expression here that show, that show the propagation speed relative to the mean velocity and temperature, and well, it allows you to determine the flame speed. Basically, this relation, okay, determine for you the propagation, the flame speed if you know the mean velocity, and the mean velocity is related to the pressure. In a Poiseuille flow, the mean velocity is the mean, meaning you integrate across the channel, but y, you depend on y and so on. So if, for example, it's closed at one end, then this relation tells you the mean velocity here must be 0, so to accommodate the condition at the wall. And so the propagation speed is 1, which means the flame propagate like laminar flame speed, a planar line. If you close it at the other end, then U must be 0 on the burn side, so it propagates like the spherically expanding flame, where the velocity on the burn side remain at rest, and so the propagation speed goes like sigma times SL, and this is the flame position. We have seen that before. But what's interesting is when you allow it to be open on both ends, since the pressure, even though there is a pressure that gets built here on both sides due to the flame, it's not a pressure buildup as closed before, but that pressure has to go at the end of the vessel and to accommodate the atmospheric pressure. And so that lead to an acceleration of the flame. In the flame, you see the position accelerate like e to the Q, heat release, laminar flame speed T, divided by L, of course, depend on the length that this is. And we have seen that to be also the case numerically, as you see in this picture, and that's where I will end my talk. Those are the analysis for small a that I showed you just before, the exact or the simpler analysis. And the other curves that you see here is for a equal to 10, which of course is not small as I assumed, so it's obtained numerically, integrating the equation. The interesting thing is that the flames start propagating relatively faster and faster, but in a linear fashion, and then come a point that there is a very quick or sudden acceleration of the flame. This apparently has been observed, and this is just a picture to show you what happened. Those are streamlines relative to the flame or not relative to the flame. So you see, because the gas is nearly zero here, then when it expands, because this is the gas get compressed, then it acts on the flame like in a stagnation point flow. There is a straining rate, and that causes the acceleration. Anyway, I wanted to show you just the phenomena that is observed, and let's take a break, and we will come after the break into a slightly different discussion. I think it's ignition and extinction.